Let me get my team up. All right, hi folks. We are now live on Twitch and Teams. I'll give a couple minutes for people to join. Dawson asked about a general rundown. Hello. Of the topics. Hi. Okay. And Corey had a question about a homework problem. There we go. Okay, so Dawson asked about, see here. Not yet. Let me invite him. Okay. Corey, what was the homework question that you had? (14B). Okay, let me pull that up. All right, so just a reminder for everybody, this is sort of replacing when I walk around and help people. So I'm hoping not to like do problems for you, especially because you get credit for doing the problems, but to kind of help you if you are stuck somewhere. So Corey, if you can tell me what your approach was. Okay, 14B. Aha. Okay. So your curious exam going to be this? Yes, it's the same way. You're going to write them down, take like a picture or do cam scanner or something, and then upload. So this will actually be a little easier to handle than the previous one, because for the midterm, it was like 2 separate assignments. For this, it's like one. You see the test, take the PDF, and like submit it in the same Canvas assignment. Okay, let me just show you my screen. Okay, you tried doing FD cosine theta. Okay, so the issue here, so Corey says he tried doing FD cosine theta for 14B. The issue here is that what's cosine theta? Because it's 30 degrees above the I direction, but in that FD cosine theta equation, it's the angle between F and delta R. So if you have, what was our F was 20, negative 14. Let me fold this down. Answer sheet being posted for us to print out, yeah. Okay, 20. It was minus 14J. So that is 20 in the horizontal direction and 14 down. So this is our force vector. And then it asks you to find the work if it moves a distance of 8 meters at a 30-degree angle above the positive I direction. So it's moving, delta R is 8 meters, and this is 30 degrees. So if you want to do FD cosine theta, you would have to find this angle theta. Does that make sense, Corey? Awesome. So that's a thing, common thing for students to have issues with. Yeah, there's nothing for you to print out. It's just the test sheet. Oof. Anybody got anything else you want to talk about? Alternately, we can do some of the practice quiz questions, sort of a random assortment. Those I'm happy to kind of do or work through with y'all. General run through the topics. Okay. So general list of topics. So hopefully everyone saw on Canvas that this includes circular dynamics. So this is things like orbits, cars driving in circles, things being spun on strings, things that are at an angle, like banked curves, strings where it's like hanging down at some angle as it spins around in a horizontal circle. And then also the stuff we talked about from quizzes 317 and 319, I think they are, which was stuff like your apparent weight, with some due to some acceleration. We talked about like cars going over hills, minimum or critical velocity. That kind of stuff. Okay, a couple questions while I was writing this down. Yes, the exam is in the recitation course. It is not going to cover springs. Okay, and then Nate had a question on 11D and Jack had a question on number 1. Okay, I'm just going to keep going and finish this up. Remember the key for circular dynamics is basically F net equals MAC. That's our golden rule. This applies for pretty much everything. If you can do a free body diagram and find F net, and if you can do circular motion stuff to find AC, put them together, that's it for basically all of these questions. Okay, then it's impulse and momentum. So this is like, oh, there's a force versus time graph. And then there's impulse is change in momentum. And then there's things like collisions. Specifically, there's inelastic collisions, where momentum is conserved. There's elastic collisions, where momentum and kinetic energy are conserved. There's two-dimensional collisions, where they like bounce off in different directions, right? 2D collisions. And then there's also work and kinetic energy. which is this idea of K being 1/2 mv squared, and your net work done by all the forces is the change in kinetic energy for your object. So this would be work done by gravity plus work done by normal plus work done by, I don't know, tension, work done by a push, like whatever your works are in your question, delta K. And that we get work, the long answer is it's the path length integral. The simple version is that it's F delta R cosine theta, or you might see it as a dot product. Dot products are included on the test. Okay. And I think that's kind of the end. Yeah. All right, so Jack said you were having issues finding impulse for number 1. Number 1 is a graph. So generally, what do we do with graphs? Could I scroll back up for a second? How far back up? So Jack, tell me what you did for number 1. Don't know what that was. I don't know why this is Sonic the Hedgehog. I actually had Sonic the Hedgehog years ago before the movie was even announced. So my students several years ago wanted to do a problem with Sonic the Hedgehog. So both triangles? Did you divide it into 2 triangles? Because that's fine, you can do that. Okay. The biggest error that students make is they forget that this time is in milliseconds. Or they measure this horizontal wrong. Remember, it's not going to be 14, it's going to be from 5 to 14. Those are kind of the 2 biggest errors that students make. Yeah, milliseconds. I underlined it, and I put it in a box and everything. Okay. I'll bold it and put it in italics next time. I sometimes do that on a test, and I don't know. I still think it doesn't help. Is it all caps? Okay. All right. So Jack, you try it from there. Nate, you had a problem with 11D. Okay. Tell me what you tried for 11D, or what you were thinking. 2 times with 2 different methods, got the same answer with both being wrong. Okay, share maybe one or both of those methods. Okay, second method, found the change in KE. Okay. That sounds good. And what did you get? My calculator. Because I feel like that method should work. How's my sound quality, by the way? Yeah, maybe. Well, Gory, you were right. Is this any different sound quality wise? Womp womp. That's how they get you. So here's a lesson. Ooh. Sorry. My sleep schedule is a total mess. I didn't sleep well last night. um, what was I going to say? Yeah. If you wrote that, oh, husky. Oh, my neighbor's cute husky. I like a cute husky. If you wrote all that down when you were doing the work, yeah, that's right. You would be able to see, oh, you put in 3.5 instead of 3, and you would lose a couple points. If you just put down the wrong number, you would lose all the points. So, any other questions about stuff? That's a good question. Should it be positive or negative? What do the rest of you think? Should this work be positive or negative? Oh, good lord. Okay, cool. So it's negative. Let's get a couple more thoughts. All right. I'm not going to say one way or the other immediately because I've got about 7 or 8 people here, and I want to see if they have anything to offer. I'm very, I don't know. I don't know if sleepy is the right word. We are looking at 11D, and we are currently talking about whether that will be positive or negative. Literally 95% of your issues are just identifying what formula to use. So that is a really good question. So, all right, before we talk about that, yes, Cole and John, you were right. It is a negative because friction is removing energy. So it is causing it to go slower. So it's negative work. And because the force and the direction it's moving are going to be in opposite directions. Right? So our cosine of theta, oh, it does. Whoops. Let's see if I might need to fix it. Whoop, whoop. Oh, yeah, you're right. It should be negative. Work done by friction. I'm sorry about that. It should be negative. Whoop. I will post a little announcement about that. Are those power problems going to be on the test? They are certainly fair game to be on the test. I will not answer you about whether it is or is not. Okay. So let's talk about how we know which equation to use. Don't need that. Identifying the equation. So I would be careful about focusing too much on identifying which equation to use. Yeah, that makes sense. So Pablo says, I'm still confused about why work values are represented as being either positive or negative. Work is being treated as a scalar value. It is scalar, but scalar can be positive or negative. It just can't be left or right or up or down. Does that make sense? It's strange. Like positive and negative does kind of indicate a direction in some sense, but it's more about, it's still considered scalar, right? Yeah. Like temperature, it can be plus 70 degrees or it can be negative 30 degrees, but it still doesn't have a direction. Does that make sense? Okay. So identifying which equation, I would say a better tactic is to identify concepts. So you might take a look at a question and be like, oh, this is Pablo, yes, you are correct. Yeah. So you might look at a question. Let me actually pull up the class and see if I can generate a random set of quizzes. So you can look at a question and say, is this momentum? Is this work? Is this circular motion? Right. And then my second tactic is to ask myself, like, what if or why questions. And then ask, what if or why questions. So these might be like, if it says, oh, well, let's look at some problems and see. Let's take a quiz. Okie dokie. Car heading north at an intersection collides with a truck of the same mass as the car heading east. So car heading north, truck heading east. They lock together and travel a certain distance just after the collision. How fast was the car initially traveling? So what concept would this be? I don't remember Cuban Dragon, who that is on Twitch. I'm sorry, I've forgotten your name. But was it Michael? I feel like it might be Michael. But yeah. Okay, sure, Nate. Nate, if you actually put it in the chat, I might be able to just type an answer. What concept would we say this question is? Gabe. Yes, okay. Sorry. I'm really bad at remembering people's Twitch handles. So Gabe, what do you think, if you had to say in like one or two words, what concept would this be? Okay, I have a couple of thoughts from Twitch, or not Twitch, Teams. Angular momentum. We haven't gotten to angular momentum yet, but momentum, yes. So for momentum, we have it's definitely a momentum question. It is a collision question. Cole and Dawson both suggested elastic. It is not. It is an inelastic collision. How do I know that? No, I don't want it to go here. I got them backwards. Gabe, you're backwards. They do stick together. They lock together and travel at the same rate, right? So because they stick together, that means inelastic collision. No, inelastic is where they stick together. Yeah. So that's, we'll put a little note here. Inelastic collision, let me put it back up here, right? This is if they stick together. This is max energy loss. Elastic is they bounce off and keep all the kinetic energy. And then there's sort of the in-between where it'll lose some energy but not maximum energy. Okay. So, all right, so this is good. We know it's an inelastic collision because they stick together. Tell me if this is hard to read. I really like this sort of pen, but if it's hard to read, let me know. That's a good idea, Dawson. I can do that. Okay. What do we know about inelastic collisions? Well, we know they stick together. What else do we know? You have to use a special equation. So I would like, yes, I would like a little more general, like in an elastic collision, we know that this happens, or we know that we're interested in this concept. For example, we're interested in momentum, right? So John has pointed out, we know that momentum is conserved. So we know it's a momentum question, and because it's an elastic collision, we know that momentum is conserved. We know that kinetic energy is not, right? So then we think, okay, momentum is conserved. That means the sum of the momentum before is equal to the sum of the momenta after. So P initial 1 plus P initial 2 equals, and these are vectors, P final 1 plus P final 2. Okay, this I think is on the formula sheet. Not 100% sure. I don't know where I have the formula sheet. I think it's in spring 2019. There we go. where's the formula sheet? There should be a copy of the formula sheet on Canvas. It is also in the test file. If you scroll down, it's all the way at the bottom is the formula sheet. Yeah. So yeah, if you look in modules, so you might notice momentum conservation is not one of the equations on the formula sheet because it's like Newton's third law. How would you put Newton's third law on a formula sheet? It's hard to put it on a formula sheet and have it make sense. Right? Newton's third law is that forces are part of a pair, right? It's just, how do you write that as a formula? It's hard. So this is one where your formula comes from your understanding of the concept. You know that momentum is conserved, which means momentum before is equal to momentum after. Does that make sense? Does that help? I think, Gabe. So then it becomes, oh, okay, I plug stuff in, I solve. I know these are vectors, so I have to do x and y separately. One thing that I talk about is to help you is also asking yourself these what if questions. So the question is asking how fast was the car initially traveling? And the information you have is about what it does afterwards. Why are those connected? Well, because if you have one car driving this way and one car driving this way, right? And they collide and stick together, and then they go off in some new angle. If we make the bottom car go faster, right? This is like a what if question. What's going to happen to the result? So we have, let's say this is, I don't know, V naught, and this is 2 V naught, but this is the same V. Would it go in the same path? Ooh. Go away. Would it go more to the east? Would it go more to the north? Would it go in like a curved path? Like what's going to happen? Tell me what y'all think. I'll give you a hint. It's not the curved path. I'm going to call this A, B, and C. Tell me which of these is probably more likely if you double the speed of the car going north. Jack, you're still having issues with one. It's going to do the same thing. If you had, okay, what if the bottom car is not moving at all? It's just sitting here, and then it gets hit from the side by the truck. Is it still going to go in this same direction? No. So clearly what the bottom car is doing will have an effect on what a combined do when they stick together. So in this case, where the bottom car is not moving, its new path is just going to be straight this way, right? Clutch. Okay. So when the bottom car has a really low speed, it goes straight horizontal. If the bottom car has a little bit of speed, it's going to go a little bit above the horizontal. The faster this car goes, the more it's going to like deflect the path of that truck. Does that make sense? So if we come back here, I'm going to tell you it's not B. What do you think the answer is? I have one thought from Teams and Twitch. Might just be lagging, I'm not sure. Okay. 2 votes in Teams. Nobody on Twitch. All right, well, you're correct. The correct answer is A. So clearly, the angle that it's going to go at depends on how fast this original car is going. There we go. Yeah, I think Twitch is just lagging. So faster car means greater angle. Okay. So then you're like, okay, these are definitely connected. How are they connected? They're connected through our momentum conservation. So I know that my initial x equals p final x plus, and this is just one object, p initial y plus p initial y equals p final y. You can get p final x and y from doing mv for the final, right? So it's going to be whatever the combined mass is, and then it's going to be v cosine theta and m total v sine theta, right? And then these, we have this, we have this, we have this. We're solving for this. We have everything we need. Does this make sense? So it's think about it more in terms of the concepts and the ideas rather than just trying to pick an equation. Let's see what the next question is on here. Ooh. Okay, conceptual question. So I don't understand how you're supposed to answer this because like there's only one answer option. But there's 2 parts to the question. I didn't make this. We got this from somewhere. Okay, let's just look at this. So this is a conceptual question. You don't have to do any math. So that's good news. 3 cars are moving with the same velocity when the driver suddenly slams on the brakes, locking the wheels. F has the most mass, H has the least mass, and all cars have identical tires. Which car travels the longest distance to skid to a stop? Tell me what concept this question is about. Is this about circular motion or forces or kinematics or work or impulse or energy or I don't know, any of those options? This one's a little challenging because there's 2 different ways you can do it and both ways are correct. Based off momentum. Yes, so you can do it with momentum, but I would say momentum is usually like connected to either collisions or force over time, which is impulse. But in this case, the question isn't asking us about time, it's asking us about distance. So what is our concept for force over distance? Next to work, which also connects to kinetic energy. You can also do this with just forces and kinematics. That is also totally fine. Actually, might be slightly easier. So we have 3 cars. Can you tell me, let's copy this, 3 cars, F has the most mass, then G, then H. Can you tell me anything about the force of friction on these 3 cars? Is it greater for F? Is it equal for all? Is it then G, then H? Less, greater for H. See, I've made a whole nother question to help us answer this question. Okay. John has the thought. Anybody else have a thought? Yes, you're both correct. A, because our force of friction is mu k mg. So if mu is the same for all of them because they have identical tires, g is the same for all of them because we're presuming they're all on Earth. So greater m means greater force. What about the acceleration? Same options, A, B, and C. So greater for F, equal for all, or greater for H. Okay. I have one from Gabriel. What about the rest of you? Everybody's like, I don't want to say. All right. Oh, nobody has any thoughts. Also, like Nate and Jack, if you want to ask questions in the chat, you can do that. I can multitask. So for this one, the correct answer is B, because F net equals ma. The only force we have is friction. M's are going to cancel. Okay, no worries. I just wanted to make sure that you weren't like impatiently waiting. Sounds good. Okay, so they have the same acceleration. So if they have the same acceleration, they're going to have, and they have the same initial velocity. What about the distance? Will that be greater for F? Same for all? Or greater for H? This one's a tricky one. You have to like really think about it. Yeah, this is distance that it takes to stop. Okay. Dawson, Gabe, do you have any thoughts? Okay. One vote for B, one vote for A. Gabe, do you have anything? Gabe says B. Correct answer is B, because we have our v squared equals v squared plus 2a delta x. If this is the same, this is the same, this is the same, delta x has to be the same. Okay. So the correct answer for which car travels the longest distance would be D. They all travel the same distance in stopping. For which car does friction do the largest amount of work? Okay, delay on your end. Yeah, you can switch to Teams if you want, or it's fine if you want to stay on Twitch. So friction does the most work. Let's say work done by friction. How do we calculate the work done by friction? There's two ways. We can either do force times distance, or we can do change in kinetic energy. Both of these should give you the same answer. So if D is the same for all of them, but F is bigger for F, then that means more work done on car F. Same thing for delta K. If they all have the same V, the one with the greatest mass will have the greatest change in kinetic energy. So it would again be car F. All right, let's talk about, see if we can find a problem. Ooh, I like this one. This is great. Okay, a car on a rough surface inclines at an angle. You have an external force applied horizontally to the crate. While this force pushes the crate a distance of 3 meters up the incline, its velocity changes from 1.3 to 2.6. How much work does friction do during this process? Ooh, this is a great problem. I like this problem a lot. So let us practice our tactics. Can you identify the concept or concepts that you need to use to do this? question. Okay. I have one thought from John, but I'd like some thoughts. Other people who might need more practice. You're not sure. Okay. Um, so you've got this picture, you've got a lot of stuff going on. There is sort of a hint here, which is the question asks, how much work does friction do? So work is probably the right approach. You could essentially do this problem using forces and kinematics if you wanted to. Work is almost always interchangeable with forces and kinematics. But the fact that the question says how much work does friction do is kind of a hint, right? That they want you to do the work tactic. Okay. So we want to find out how much work friction does. And the information we have is some stuff about the other forces and the speed of it as it goes from one point to another. So let me ask you a what if question. If there were no friction, would this 2.6 meters per second be the same? Would it be bigger? Would it be smaller? Mm-hmm. It would be bigger because you're clearly losing some energy to friction. Okay, clearly losing energy to friction. What kind of energy? Kinetic. Do we have a connection between kinetic energy and maybe the work done by friction? Now, it might not be one explicit equation that says work friction equals KE blah, 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 but maybe there's an equation that has like a more general connection between work and kinetic energy. Nope, no one's sure. I'm not sure if this is on the formula sheet. I'm going to switch over real quick and see if I have any more, if I have any activity or anything. Nope, doesn't look like it. No, nobody has any thoughts? Getting a little concerned. How about net work equals the change in kinetic energy? Does that look familiar? Hopefully, this is one of the big equations for this section. So hopefully, maybe remember it. Okay. So net work means the work done by all the forces. So what are the forces that are acting on this box? Gravity, normal, friction. Is there anything else? And the push, right? So you can draw a free body diagram if you want. It's generally very useful. Gravity, I think it's a horizontal push. Normal, that's perpendicular. Friction, that's backwards. Push. No, that's normal. Push. So my net work is going to be the work done by each of these forces. And that is going to equal my change in kinetic energy. I know my change in kinetic energy because I know my mass and I know my velocity before and my velocity after. So on this side, it's going to be 1/2, 300 kilograms, 2.6 squared minus 1/2, 300 kilograms, 1.2 squared, 1.3. Okay, so I've got this side of my equation. So now let's see if I can fill in some of this other stuff. Work done by gravity, work done by normal, work done by push, work done by friction. If I find these three, I can solve for this one. So can you tell me any of these? Work done by gravity, work done by normal, work done by the push. One of these is super easy. Normal is 0. How do you know that? Because it is perpendicular to the motion. Excellent. Okay. How about the other forces? Let's go back and look at the problem. No thoughts? All right, well, remember we do work as FD cosine theta. So we have an incline of 30 degrees. Our distance is 3 meters. So we have force of gravity is going to be 300 times 9.8. The distance is going to be 3 meters. Theta is going to be the angle between the displacement and gravity. So it's going to be 30 plus 90. So this is 120 degrees, which makes sense because we should get a negative number. So John gets negative 4410. That sounds pretty good. Because gravity is working against the motion of the box. Okay. For the push, we have our force is 2,400 newtons. Our distance is 3 meters. Our angle is going to be the angle between our horizontal and our delta R. So this is just 30 degrees. So we end up with, switch colors because I feel like it, negative 4410 plus 0 plus work done by friction plus the work done by the push, which is 400 times 3 times cosine 30. I get 1110 joules. 1110. It's really 1111 joules equals my change in kinetic energy, which is, oops, nope. I had my calculator in radians because I was doing radians for physics 2. Should have known better. 6235. 6235. Okay, and this makes sense because we hope to get a positive number out of this. Okay, and then that equals our delta K, which we were calculating up here. Our delta K is 2.6 squared minus 3 squared times 1/2 times 300. 760? 760. So then we solve for WF, work done by friction, and we get plus 4410 minus 6235. And I get negative 1064 joules. Negative, which is good. We expect friction to be doing negative work. Hopefully that's one of the choices. That's pretty close. Some pretty severe rounding going on, but I think that's it. Significant figures. I hate significant figures. I think they're so dumb. Part of this is because when I did grad school, we didn't care about significant figures. My work was all about signal to noise ratio. So the 760 came from doing delta K. So delta K is K final minus K initial 1/2 mv final squared minus 1/2 mv initial squared equals 1/2 300 2.6 squared minus 1/2 300 1.3 squared. That should be 760. Please let me know if I made a mistake. Okay. It's all good. I feel like y'all are just kind of chilling out and watching, which is okay. I can just do some more problems. If you have questions, interrupt me. But I really like this problem. I think it's a really good problem. Ooh. Loop-de-loop. How high is it above the floor when it leaves the track? Neglecting friction. Ooh. That's interesting. Can I do one of the equations that bring in time? Let's see if there are any in here. Bum, bum, bum. None of these involve time. Ooh, that's a good one. Spring to my tongue there. 14. Okay. Does 14 bring in time? I don't think so. Oh, on the quiz. Okay. Okay, one with like power. Okay. How long will it take a 2.57 HP? What does HP stand for? Horsepower. Yep. Horsepower. And it conveniently gives you the conversion right there. To lift a 250 kilogram beam directly upward at constant velocity from the ground to a height of 45 meters. Assume frictional forces are negligible. Okay. So, so the idea about power is generally the change in energy over time. It's also, you can think of as the derivative of work over time or delta W over delta T. There's a lot of sort of subtleties here. So watts is 1 joule per second. Okay. So we have a 2.57 horsepower motor. 2.57 horsepower, which is, so this part is the identify concepts part that I talk about. And then we had 746 watts per horsepower, I think. So our motor is giving us, come on. Horse has about 2 horsepower. Yeah, which I find really funny. I think a horse can generate up to 4 horsepower for like the really big draft horses, but it's a short amount of time. It's calculated based on like the average work that an average horse can do over like an entire day or something. But I think it's really interesting that a horse has more than 1 horsepower. 746 times 2.57. Okay. So that's 100, 1,000, 19, 17 watts. So this means that our motor provides 1,917 joules every second. This is joules of work that can do something. So what are we doing with this work? We are lifting a beam up to a particular height. So we are lifting a 250 kilogram beam, lifting a 250 kilogram beam up to a 45 meter height. Okay. So how much work was required to do that? Well, we can figure out the, since it's going at constant velocity, our delta K is 0. The only forces we have are gravity and the lift from the crane. So those have to add up to 0. We know that gravity is going to do mg distance times cosine of 180. So our work done by lift must be the negative of that. So the work done by our lift must be 250 kilograms times 45 meters, times 9.8, got my G. 8 times 45 meters. And the cosine 180 is going to get canceled out because it becomes negative cosine 180, which becomes positive 1. All right. So in order to lift that up, we had to do 250 times 9.8 times 45. Ooh, 1110,250 joules of work were required. So if we can provide 1917 joules every second, we just divide joules divided by 1917 joules per second gives me 57.5 seconds to make that trip. Does that make sense? So power is about how quickly you can do work. This amount of work has to be done regardless in order to get that thing up. You can either do work very, very slowly, like 1 joule every second, like, right? Or you can do it more quickly, right? And that has to do with how much energy that motor is capable of providing in a certain amount of time. Dawson, did that help? Hopefully that's one of the answers. It is, thank goodness. 7.5. Okay. Anybody else have any particular questions? I like this problem. I like this problem. I like that problem. I like all of these problems. All right. Well, if no one has any questions, I might just sort of work my way along here. Figure a very small toy race car is released in the loop-de-loop, released from a height 2r above the floor. How high is it above the floor when it leaves the track, neglecting friction? So we have car loop-de-loop, car loop-de-loop. Okay, and it starts at this height, 2r. This is, oops. Yeah. Okay. This is 2r. This one I'm not sure about. Because my mental thought is of one way to do it, but it's not the right way to do it. I did already go over 11D. Let me scroll back a ways. 11D, I think the key was, I didn't actually write anything down for that. Remember that one was the one I think we fixed. It was supposed to be negative. Is it? Or is that the other one? Yeah, that was the one that was supposed to be negative. Yeah. Okay. So I did it wrong. I have to fix that. So my intuition for this question is that, oh, well, it would go up. It has some potential energy, would turn into kinetic. As it goes up, that potential energy would turn into kinetic. And so it would eventually, like, it would all be potential when it gets back to the same height. But that is the height where its velocity would be 0. But I don't think that's the height when it leaves the track. So the height when it leaves the track. So this is one of those conceptual things. What is the concept here? Leaves the track means the normal force is equal to 0. Okay. And so the normal force is always going to be inward. Okay. Normal force is always going to be inward. And so it's upward right here, it's inward right here, it's inward right there, inward right there. Okay. And so at any given point, it has a normal force going inward and it has a force of gravity pulling down. This is really challenging. I don't think this is the right way to think about it. N equals 0. Maybe it is 2r. I feel like it's not 2r though. Thinking about this. Because there's a way to do this with classical mechanics, but it's a lot harder. Track means n equals 0. Okay, I'm going to do it the long way and see if I get the right answer. This is theta. We're going to solve for theta, I think. So you have n cosine theta has to equal mg. You have n sine theta has to equal mv squared over r. Okay. So to get n equals 0, only happens at the top part. That's not right. Yeah, it's because you can't divide it like this. That's not the right way to do it. I think you have to do like that. You have to do this as theta. Okay. So it becomes n. I might skip this one and come back to it because this is a little bit challenging here. Okay, whatever the normal force is going to be normal force minus mg cosine theta. So I'm taking this inward component and this outward component. Yeah. I think that works. I feel like there must be an easier way to do this. Yeah, there is not one like this on the test. I gotta think about this. It's really tricky. Okay, we're gonna skip and come back to it. Okay, but I am gonna come back to it because I'm stubborn. Okay. Bullet shot vertically into a 3 kilogram block. Block lifts upwards 4 millimeters. So it just kind of goes. Bullet penetrates the block and comes to rest in a time interval of 0.0010 seconds. Constant during penetration. I don't like this problem. I think it's really like written really badly. It's hard to work out what it's asking. So I'm going to skip that one. Balls turn upward at an angle. Okay. That one's super easy. You can do this one with kinematics. 620 gram object traveling at 2.1 meters per second collides with an object. Okay, here we go. Ooh. And then we have a vector problem afterwards, Gabe. So that'll be good for you. Okay, so we have a 620 gram object traveling at 2.1 meters per second. And then it collides head on with a 320 gram object traveling the opposite direction at 3.8. So 320 grams, opposite direction at 3.8 meters per second. What is the change in kinetic energy of this 620 gram object? So we know it's an elastic collision. That's great. That identifies the concept right off the bat. What do we know about elastic collisions? We know that energy is conserved. So does that mean the answer must be D? It doesn't lose any kinetic energy? No, because it's the total kinetic energy. So Nate asked if there's multiple ways to solve either kinematics or force. You can do it however you want. Yes, unless it specifically says that you have to do using work and energy. If it doesn't say specifically, you can do it however you want. Which is a good point. I might need to fix the question. Okay. So we're interested in the change in kinetic energy for the 620 gram object. So we're going to focus on this one. We have the kinetic energy initial is 1/2 0.620 kilograms times 2.1 squared. Kinetic energy final, we will have to figure out. We don't know. So this is where we hop over to our formula sheet because we remember that elastic collisions have their own special equations, which are these equations. Since we actually only care about one of them, I'm only going to use this first one. So can I whoop, not what I meant to do. Select. Copy. Interesting. Can I paste it? No, apparently not. Yep. Okay. So our V final X is M1 minus M2, M1 minus M2, M1 plus M2. This is V final for number one, the initial for number one, plus 2 M1 over M1 plus M2 V2 initial. Let me double check. M2. Is that what I wrote? M2. So I told Nathaniel that if it doesn't say, you can do it whatever way works. If it says you have to use work and energy, then you have to use work and energy. So this, because I have chosen my 620 to be number 1 and my 320 to be number 2, this is 620 minus 320 over 620 plus 320. My V initial is 2.1 plus 2 times my 320 over 620 plus 320. And my V2 initial is negative 3.8. Why is it negative? And 40, okay. So this is 300 over 940 times 2.1 plus 640 over 940 negative 3.8. I get negative 1.92 meters per second. So the negative means it's going in the negative direction. So we find that this one bounces off. So it bounces back at 1.9 meters per second. But the negative actually doesn't matter because we just want to do this and then we subtract. So 2.1 squared minus 1. I get 0.224. Is that one of the answers? Loses 0.224 joules. Yes, haha. Close enough. Okay, a force acts on an object. How much work does this force do as the object moves from the origin to a certain point? Ooh. Okay, this does require you to do one extra little thing, which is turning your R into delta R. But the first question is, what is the concept? This is a really easy one because it says work. We're looking for work. We have a force and a displacement, so we want to do F dot dr. So change colors because I feel like it. So we want work is F dot delta R. When we have vectors, it's x components plus y components multiplied together. And note, we have to make sure that it is delta R, not R. So they give us R, but it's from the origin. So we end up getting delta R is the same value, but might not be that way. So it's 13i plus 11j. 13i plus 11j. Okay. And our F was 12 and negative 10. So this becomes 12 times 13 plus negative 10 times 11. So we get 12 times 13, 156 minus 110, I get plus 46 joules. Note that this is a scalar. A dot product is also called a scalar product. It is just a number. Let's see if that's one of the answers. Yes, 46. Phew. Phew. Okay. Here's another vector one. What is the angle between these two? So Gabe, you were interested in the angle. So can you tell me how you might approach this problem. Or not. I don't even know if anyone's watching anymore. I always get confused with these problems. Okay. So this one, you want an angle between two vectors. There's a couple ways to do this. The easiest way is to do the dot product. How to remember that? I feel like the tactic might be, okay, this is a vector question. What are things I can do with vectors? I can add them, I can subtract them, I can do dot product, or I can do cross product. And then you say, okay, which of these is going to give me an angle? And so, okay, well, adding and subtracting doesn't really get you an angle, but dot product or cross product will get you an angle. And then the question is, which one is easier? And for this class, we've only talked about dot product so far, and you can do this with cross product, but it is beyond the scope of this class. So the answer is you want to do a dot product. So plus 4 minus 2 minus 2. So why is that? So we have plus 4 minus 2j minus 2k, and we want the angle with the positive y-axis. Okay, this is A. So dot product of A dot, the positive y-axis is basically j hat. This is kind of weird. It's going to be A j hat cosine of the angle between them. Hey, the angle between them, that's what we want. So if I can find these two and I can find the dot product, I can solve for cosine theta. So how do I get the dot product? I can use my other tactic. So this would be ax times my x component of my y vector, right? So my j vector is 0i plus 1j plus 0k, right? So if I do plus 4 times 0, I get 0. I do minus 2 times 1, I get minus 2. I do minus 2 times 0, I get 0. So this is minus 2. This is going to be the magnitude 4 squared plus negative 2 squared plus negative 2 squared. It's the whole three-dimensional thing. The magnitude of my unit vector is just 1 cosine theta. So I do 16 plus 4 square root. So I get 4.9 cosine theta. So cosine theta is negative 2 divided by that number. So divided by times negative 2 is negative 0.408. And then we inverse cosine, and we get theta is 114 degrees. Hopefully this makes sense. So we think about if we have x, we have y, and then we have like z coming out of the page at your face. Our a vector goes 4 over here, 2 down, and then like 2 out of the page at your face. So this angle makes sense that it should be greater than 90 degrees. Hey, that's one of the options, thank goodness. Making sense? Yes. All good. Okay, it's 3:40. So let's have a look at the remaining questions on here. If you have a question from the homework, shout it out. We have a banked curve. We have a 3-piece explosion. We have work carrying a bag. This one's really easy, right? You carry a bag a certain distance at a constant velocity across a room. How much work did you do? This actually, I'm thinking, on the bag in the process. If it's going at a constant velocity, then there's no net force in the horizontal direction. Your force is purely vertical. So you do 0 joules. Anything students have had trouble on in the past? Lots of things. I would say some of the biggest confusion has to do with like doing momentum in 2 dimensions, not just 1 dimension. Yeah, I don't know. Seems like it's always different. Are there any formulas not on the sheet that you will need on the exam? I would say that momentum conservation one, it's not really an equation, but that concept. This one, right? It's not on the formula sheet. Would there be a Ferris wheel problem? There might be. Totally fair game. How much do you weigh at the top of a Ferris wheel that's going around at this rate? Okay. So remember, like a Ferris wheel problem, you have you're sort of standing straight upright all the time. So no matter where you are, there's always your normal force and the force of gravity, right? And together, they have to create a inward force equal to your mass times your centripetal acceleration. Usually, we only ask you about the top and the bottom because then you have your normal force is upward and gravity is downward, and your normal force is upward, your gravity is downward. You don't have to worry about weird angles. So we'll very rarely ask you that. This is your weight. This is the same all the time. But your inward direction will be downward at the top and upward at the bottom, right? So sometimes you'll get, this will be positive, sometimes this will be negative. We do some of the Module 3 homework problems. I don't want to do Module 3 homework problems, but I will answer questions about Module 3 homework problems because doing them is what you're getting graded on. So this is the difference. Like if it's a bunch of us in a room, it's one thing, but doing it like recorded online, it's kind of a different thing. So does this make sense, Ferris wheel? Nate, do you have anything particular in mind for a circular dynamics problem? How do I do all the Module 3 homework problems? See, exactly. Okay, Let's hop back over here. This is a circular dynamics problem. This is a non-trivial one. Stare at that one for a second and tell me what you think you would do to start this question. I think I have an activity notice. Let me check my activity notice. Oop, cancel. I'll do that. There. All right, have a try at that one and tell me. Okay, it's not a big deal. All right. Oh, disappeared. You're confused by all three graph problems now. Okay. So the key for the graph problems is pretty much all of them. It's about the integral, the area under the curve. So tell me what you're getting for the area under the curve for, say, problem 1. While Nate stares at this problem for a little while. Oh, there's a dog pooping. Strange, that makes me miss having a dog. 270. So Nate, you're close. Not angular acceleration, centripetal acceleration. But yes, I think you had 270. What was the question? So one thing to keep in mind, Jack, is that it is sign dependent. So you should have a negative number because it's below the x-axis. So it would be 1/2 times 30,000 times 5, 6, 7, 8, 9. Let me hop back over. Okay, it's negative. Where's my calculator? What were we doing? We're doing 1/2 times 30,000 times 9 milliseconds, which is 0.009. I get negative 135, Jack. So I feel like maybe there might be an issue with how you're doing the area of a triangle. Because it seems like you're getting twice what you should be. There you go. Okay. So then what are you doing with your negative 135? Okay. There you go. So you had the 2 mistakes and you just swapped them. Okay. Nate, did you get, the centripetal acceleration? Okay, don't let me rush you. Yes, v squared over r. So you got to find r for this one. Yep. So it would be 1 squared minus 0.5 squared is, I get 0.866 for r. So then it would be 7.5 squared over r. It's really fast. Okay, so what do you got for your centripetal acceleration? Can I make this half size? Okay, and then bring up my OneNote. Should have done this in the first place. Yep, that is also what I got. So we have, this is r, this is 1, this is 0.5, 0.866, and we have v is 7.5 meters per second. How do we know it's v and not omega? The units. It's meters per second and it says speed. So we do, whoops. So v squared over r equals AC, so that's 7.5 squared over 0.866, get 64.9 meters per second squared. Okay, then what? Okay, so we know our force, F net, is mass times acceleration, so 0.71 kilograms times 64.9, and so we get, you said 46, sounds right. Okay, so that is our net force, but it's not what the question asks. What does the question want? Tension. So how do we get from the net force to just that tension? You dislike tension. That's okay. Remember, tensions is whatever it needs to be force. So what is the thing that I recommend doing when we have force problems? No, it's not being distributed evenly because you got to worry about gravity as well. Good thought, though. Sorry. I would draw a free body diagram. So I have tension this way, I have tension this way, and I have gravity this way. This is going to be slightly less, right? So, so we have tension 1, tension 2, and gravity. And we know that if we add these up, we should get our net force. And we know that our net force is negative 46.11 newtons in the I hat direction and nothing in the J hat direction, right? Because this is inward, which for us is this way. Okay, so this is 0I minus 71 times 9.8 is 6.958 J. Okay. T2 is going to be whatever it is times cosine of our angle theta, which we know our angle theta is 30 degrees because we remember our special triangles. And this is minus T2 cosine 30. Didn't leave myself a lot of room here. This is going to be negative T1 cosine 30 minus plus T1. One of these should be sine. This should be sine. Okay. Hopefully all this looks familiar. I pull out two equations, negative T1 cosine 30 minus T2 cosine 30 equals negative 46.11 newtons. And then we have T1 sine 30 minus T2 sine 30 minus 6.958 newtons equals 0. So I have two equations and two unknowns. Solve. So I don't know how you want to do this. There's lots of different ways to do this kind of thing. Neither one is particularly easy. What I might do is pull out and then here pull out so I end up with T1 plus T2 equals 46.11 divided by the cosine of 30 gives me 53.24 newtons. And then T1 minus T2 equals 6.958 divided by the sine of 30 is 13.916 newtons. And then I add both together, so I get 2T1 equals 67.16 newtons. So the tension in the top string is 33.6, and the tension in the bottom string, I can plug this back in and get 19.66. So it's not half and half, sadly. Let's see if that's one of the options. Yes, 34 newtons. Boom. I'm very proud. Yes, if this were on a test, it would be a long response. But the thing to keep in mind, there is nothing in here that you do not know how to do, right? You know how to set up your free body diagram and do those forces. You know how to solve a system of equations. You know how to get the net force. You know how to get the centripetal acceleration. It's not bad, it's just tedious, yeah. As long as you understand how, like, these charts that I like to do work and the general idea of how forces balance, then I think it makes sense. Yeah, takes a while. All right, it's 4 o'clock. I am getting sore throat from talking. Anybody have any questions? If you have specific questions about specific homework problems, I did not go from that. The negative 6.98 is the force of gravity, mg. The 46.11 is the centripetal force. So they both came from different places. Okay, how would you do the rocket package? Number 7. How did I get it? It should just be mass times gravity. 0.71 times 9.8? Or did I make a mistake? It could be a mistake. I make mistakes all the time. I'm human. Okay, rocket package. So rocket package, actually, I think, Pablo, you and I have talked about the rocket package a couple times. So person whose name I presume is Chris. I can't remember who's got what Twitch. Is it this one that you're talking about? Number 7. Yeah, the mass is really teeny. Tell me what you were thinking. If you were not thinking anything, tell me about what concept you think it is. It might be more than one concept. Okay, so it's the inelastic equation, right? Because they stick together. You said, oh, wait. Good, it's not elastic. You want to use an inelastic. So part of it is a momentum part. You have a rocket that hits a package and they stick together. So that's momentum conservation. But what about the rest of the problem with the explorer and the river and all this kind of stuff? It would not follow a straight hypotenuse. You're exactly correct. What shape would the path be? An arc? Arc sounds like it's part of a circle. Parabola. Ooh. So you have two parts of the problem. You have a momentum conservation part and a projectile motion part. So you can sort of think about in order for in order for it to reach the Explorer, if its initial velocity is too short, it'll go meow. If it's too high, it'll go woo. So there is a sort of a too high is fine. You need a minimum speed. The minimum speed is going to be where the parabola just reaches this guy. So this is like projectile motion. What initial velocity does it need to have in order to travel 30 meters horizontally before it has traveled 200 meters vertically? And then once you have that, then you can do the momentum conservation part and figure out, okay, if the rocket is coming in and hits the package and then they stick together, how fast must the rocket be going to get us this V naught for the combined structure? Does that help? And Pablo, we talked about this question. Does this one help for you as well? Then I might have to go. I'm getting really tired. My throat's starting to hurt. Distance equation, the one with gravity. You have to use x and y. So you would need to figure out using y to get the time and using x and the time to figure out the horizontal speed. So this is, you got to think back, way back to projectile motion. You can do the range equation if you realize that it's half the range. That if something is launched horizontally, it's not a good color. If something is launched horizontally, that's the same as starting at the halfway point. So your range equation, you would do 1/2 r. So you would have the 30 meters is half the range, and your range would be your v squared sine 2 theta over g. But you don't know theta, so never mind. That's not a good plan. I would just think about, okay, you drop it off the cliff. How long does it take to hit the ground? Okay, that's how much time it takes to go the 30 meters. So how fast does it have to go? So Pablo, what might help for you is to just erase all of your work, start on a clean sheet of paper, and act like you've never seen it before. Because if you're going back and correcting and going back and correcting and going back and correcting, you start to lose track of what's right and what's not and where things came from. But yeah. All right, thanks, y'all. I will be checking email for the rest of the day up until the test. Definitely ask me if you have issues. So, all right. Thank you, everybody. Have a good day. Good luck on the test. Yay. I'm going to sit and look at that question because that's really challenging. All right, bye, y'all.